Or any questions, comments? We start talking about optimality conditions or other optimizing problems. So for the moment, everything general. Whenever I want to say specific things about convex concept, I'll make it special. So F for the moment is any function. Not necessarily convex. Problem with this is that X can belong to all of Rn or X will belong to some convex at X. Those are the two kinds of problems we're interested in this class. This is called unconstrained. What's the difference? Why are you able to study that? Is there a reason I'm making this distinction?
If you take the convex set, be bounded, then it will one is optimizing on bounded domain, and another is unbounded.
So, what's the big deal? Why am I making unnecessarily complications? I could have just set constraint and let this become Rn in some special case. I can take X to be Rn in a special case. Question detail. Could be a problem unconstrained constraint. Something will happen here which will not happen.
So suppose the curve, that the function, the surface, it might have a global minima, but we are looking interested in global maximum.
That's not a problem.
Like in the unbounded domain, it will run into infinity, but in the bounded domain, it will not.
What is the problem? What am I interested in? Trying to find the minimum of this functionality. In the unconstrained world, what do you expect? So, X star or X star will typically be minimum one, most throughout the class. So, X star for the unconstrained problem, X star for the constrained problem. Will it be quantitatively different? It might be depending on X. Capital. For example, we think that capital. You can give it any form.
Like in the first case, it might not even exist sometimes.
But unconstrained word.
Yes.
Okay. But
Second case,
it always exists.
no. Like
You're going to be confusing this with bounded. Finite.
Constraint is not necessarily bounded or even continuous. It could be discrete as well.
So yeah. Let's keep it convex. Those are not the kind of things I'm not making things dirty. It will be convex, but it's not really strict subset of R. What do you think it's different about X star or unconstrained volume or constrained volume? If we used to finding some functions optimal, what happens? How do you find it?
Usually where the derivative.
Yes. So now, given that we have this word, could you differentiate the two? Derivative. Yeah, that's one possibility.
So even if the function is differentiable in the constraint
Given
order,
take all niceties.
and the constraint get the border conditions. eh, we cannot differentiate it at the moment.
Now you have to be slightly more careful. What does it mean by not being able to? So in this world, typically, how do you find? These are typical notion. Does it hold here? Is everybody on board that whatever we have not yet proven anything here, we'll prove all of this. That if X star is the like I have not even defined local optima, I'll define local optima, then global optima. But we have this sense for a long time that the optimal point should satisfy that the gradient be zero. But what are we assuming for that?
Towards the external from every direction.
Okay, that's one way of thinking about it. But what does it mean? It automatically means that the space over which you're optimizing is unconstrained. You're allowed to go in any direction you like. But that's only true in the unconstrained world. So what will go wrong in the constrained world?
So if we are looking in a constraint world, and suppose for some other source, we can know that we are guessing that the X star lies during the boundary of.
Why do you have to guess? Give me an example where this is not true. That would just settle all the problems.
Take f of x equal to x and the boundary as 0 to 1.
Okay.
So minima is at 0, but the derivative is non-zero.
It's as simple as that. So that is why we have to treat these two things very differently. So it should be clear why we are doing something. The unconstrained world is much easier to handle because of this condition that we will show in today's class, that if X star is local optimal, this better be true. Because I've not said anything about F being convex or not. That's why I'm using this word local optimal. I'll soon define all of this carefully. But the same thing doesn't hold in the constraint world. Something completely different will show up as a necessary condition. All right, so let's begin. Okay, so few definitions today. So first, local minimum. And throughout the class, we'll just do the problem minimize f of x. If you don't like min, you want to work with max, your problem. They're the same thing. Local minimum. X star is called a local minimum. There exists an epsilon greater than 0 such that f of x star is less than equal to f of x for all x belonging to, this is neighborhood of x star. So what is an epsilon? I want to define an epsilon. So an epsilon x star is all x such that x minus x star is less than. So that's the local minimum. So what would I define as a global minimum? Yeah, so now from local we can go to global. And here I'm not differentiating between unconstrained and constrained. The same thing holds if I just restrict here or all x belonging to capital X, where x is the constraint set. So this one not being. Similarly for global minimum. So x star is a global minimum. If of x star and we add this adjective strict local, strict global, if these inequalities are strict inequalities. Question?
Extra itself is in the.
Sorry, say it properly.
So, how can it be strict if extra is also within the neighborhood?
Eliminate that. If you want. For all x other than x. You're checking for every other point. That is equality by definition. Okay, so what are we now? The first thing you want to do is to characterize some necessary conditions for x star. Okay. So suppose I will, again, I have said nothing about f being convex. F is some arbitrary function f. It could look like this, for example. This could be f. What am I after? I'm after an x star such, which is a local minimum. Let's say. What do you think should happen? I want to characterize. I assume its derivative exists. Okay, that much I agree. First derivative, second derivative, as many words. So what everybody understand what necessary condition means. So that necessary and sufficient. For the moment, we are looking at necessary condition. That if x star is local optimal, some condition has to be true. That's the necessary part. Sufficiency is that if x star satisfies a particular condition, it's a local minimizer. That we can't get for the moment. So only interested in the necessary condition. So what's a necessary condition? First derivative 0. Why? That is more important. The answer is correct. We've all been told this for long time.
Around the surface or the curve.
I mean, there is no surface in one-dimensional function.
Yeah, around the curve.
What? Okay.
If I draw a tangent.
There is no such requirement, but go on.
So I am want to find such point so that if I move a little bit from that point, I have certain distance. So the tangent will grow from the tangent.
Why?
Basically from 0 to.
It's a weird way of saying things. What happens if it's a local minimum? Just think of it visually. I've drawn especially for some good reason this function. Tell me what are the points at which they are local minimas? I've drawn multiple such points. What's happening there? Something special is happening. That is true, but at the point which is going to achieve the local minima, what exactly is going on there?
Different.
Sorry?
I know a different notion.
Finish it. So valley is correct. You're stuck in the valley. There better be a local minima. But at that exact point, what do you visually see? Something is happening there. how
If we
the function is decreasing, then it starts to increase because that's the whole point of having a value. So there is must be a point at which something happens.
have a ball at that point.
Let her finish, I'll come back to you.
The sign of the derivative change.
Very good. So given that it's a continuous differentiable function, what has to happen? Yes, and if it is hitting zero, what is so special about that point? Before it, what is the property of all points? Negative. So it's decreasing. And right after it, what's happening? So what is the so special about that point? No, derivative change is correct. Now what is so special about that point, given that the derivative is zero? Just before the function was decreasing, just after the function is increasing. So at that point, what must be happening? Agree. Just one more word. Slope is in fact zero. What more happens at that point? So what are you trying to say? So let's suppose this is my x star. And let's call this x, anything to the left x minus, anything to the right x plus. Whatever I'm usually saying, f of x minus is greater than f of x star. Agree? And f of x plus is greater than f of x star. All of this is loose, but hopefully it communicates the point. So what is so special about x star? Isn't it a local optimum? Don't hesitate to say it. It's true that the gradient is zero, but what is the end result? The end result is that in fact, x star better be a local optimum. It's clearly not a global optimum, the way we have constructed this function. Because this happens to be true here, this happens to be true here, and possibly so many other places. Okay, now you come in.
So if we just forget about the mathematical term,
Okay.
we have points. So suppose we are putting a ball.
Hmm. Which curve should I put a ball in? This is a function.
Yeah.
Where should I put it? Tell me.
So on the x star, we are looking at interest in x star. So if I put a ball there and try to
how do I put a ball on a function? I can put a ball here. Put a ball function, right?
like that, suppose is as a roller coaster.
I don't know how to put a ball. That's what I'm asking. I can put a ball on the domain. That I can do.
Yeah, correspondingly, we can draw a ball and the f of x star.
He's not talking about intervals, he's saying about
literal ball.
I understand. I don't want to. You're thinking of tubes now.
No, not tubes.
What will they look like?
And I'm saying, suppose someone is
Oh, okay. I understood. No, don't want to go down that path. You're saying it's going to go there and sit there.
yes.
That's the physics way of looking at it. That's where the name stationary point comes out. Okay. So now that we know what is going on, what do we want to show? That if x star is a local optimal, then the gradient of f at x star, sorry, this keeps happening, is equal to 0. How do we build as proof? The intuition is there on the board. Remember, this is unconstrained world. You really have one thing to do. I want to prove something in terms of the gradient. What connects the gradient with the function? You really have one thing. What's a universal fact we know which relates the function values to the gradient? Line joining what?
X star and X minus or X plus. And we're trying to move the
The
X.
function is not convex, so that won't typically help you.
Yeah, but the chord, whatever you're getting,
It could be above it, below it.
yeah, that is fine. But at that point, as in the limiting case as X minus or X plus, it will be it identical with the slope.
Mhm. So,
That is exactly that we
so you have to formalize whatever you're saying.
yes.
But there is only one thing really we all do to connect functions with their gradients. That's a Taylor series approximation. So, can somebody tell me what should I do? How should I use really the Taylor series? See, anyway, I'm only interested in the local neighborhood. I'm not interested in the global optimizer. So you can take things small enough, close enough. You can do whatever you want. Because my definition of local neighborhood, I didn't specify an epsilon. There exists an epsilon. That's all I specified. So you could choose whatever, however small there is. You don't have to have for all epsilon. That's true.
If I do the small epsilon greater than 0,
Yeah.
and I'm looking at the Taylor series expansion around X star. So I will do that f of X plus X star plus epsilon equals to f of X star plus epsilon into f prime of
Grade F or grade, yeah.
and so on. And
Okay.
others, if I take that epsilon tends to 0, all the order of epsilon square term will be negative. Like we can make it 0 or negative, approximate it, and from there we can just see that f of x star minus x star plus epsilon minus f of x star by epsilon equals to grad of f of x star.
But this is in one direction.
Yeah, from other direction also if x star minus epsilon.
Okay. So more or less the same idea, just that we want to do it in n dimensions rather than just one dimension. You can do it straight away. So let's define. So what do I want to show? I want to show this. Okay. So if x star is local min of f, then the gradient of fx star is 0. Okay, so define proof. Alpha to be f of x star plus alpha d. So d is some direction. So d belongs to Rn. And alpha, we'll take alpha going to 0. Positive, but alpha going to 0. So think of alpha small, d is any direction. All right. Now the fact that x star is a local optimal, what does it tell me? That f of x star plus alpha d is greater than equal to f of x star for small enough alpha. That's just by definition. So if I take the limit, what is this equal? This is definitely greater than equal to 0, right? But what is this quantity equal to? We did this in earlier class also, which I left it as an exercise to show this is equal to. Sorry? Yeah, so it is del fx star times d. Okay, so now can somebody conclude? I claim I've shown everything. For the moment, I've only shown greater than equal to. I'm leaving a punchline to show equality. Why should it imply equality?
On the other part,
Tell me what the other part.
will be x star minus alpha it equals to
Sorry, alpha is greater than 0, small enough.
Yes.
That you are frozen.
Yes.
So what does the direction mean?
So that yes, the other direction, you have a minus sign limit that is greater to 0.
Say the right thing. That's not good.
Yeah, so gradient f star d is greater than equal to 0. And since d is any arbitrary direction, if you replace it with minus d,
That will work. So D should be replaced with minus D. Is it okay? Because D is arbitrary. For any D, I've shown this. So it's true for minus D as well. And that will change the sign. So we essentially have equality. In one dimension, there's the same meaning what he said. You come from the left or you come from the right. First, I'm coming from the left, then I'm coming from the right, and they're all equal. In multi-dimensions, that left-right doesn't make any sense. So that's why we're picking an arbitrary D. These are called first order conditions because of the first derivative. Now we look at the second order as well. Next, assuming Hessian exists. So assuming Hessian exists, we have the lemma that if X star is a local minimum of F, then del square F X star is positive semi F. You might don't confuse it with convex function. We showed something similar that the Hessian of a convex function is positive. This has nothing to do with convexity of F. All it is saying is that if X star is a local minimum of F, then the Hessian in fact is positive semi-definite.
Having global minimum. Is it always the case that there is a small neighborhood around x star where f is convex?
You would like that, but you're close to like it. See, for the moment, I'm assuming continuous everything, but it's not necessary, right? It could be local minimum. Just above, it can have discontinuous jump. It can lose all its convexity. For a nice enough function, if you throw in few derivatives, possibly that is true. But it won't help you in what we are trying to do. You might get stuck up. So what you're essentially saying is this kind of function where suitably small neighborhood, it's convex. Could be true. But yeah, not very useful. But you can construct examples where it is not. Okay, any idea what should we do?
Take the help of the tailors.
Okay, and then do what?
How we remove the order of pixels, but
Remove.
like I will neglect that.
Mhm.
And since the local minimum, that first order will be 0.
Yes.
And from there we can so the field.
Okay. From the Taylor series again. Okay. That far we go directly from the Taylor series. And if I use my previous lemma, I can get rid of this quantity also because X star is a local minimum. So this also goes away. So I'm left with these terms. By definition, this is larger than this because it's so. What can I conclude about this? One more step. So this quantity, this minus this is greater than equal to 0. So alpha square by 2 d transpose that far I went. How do I conclude that this is always greater than equal to 0?
You can take the alpha square.
I can't or I can.
We can
Okay.
take the alpha square
Mhm.
and take the order of 1 plus some small term.
You can.
I have to show that the order of alpha square term.
What does PSD mean? This is a specific definition for positive semi-definite. That's all we need to show. How do I do that from here? There's nothing to be done. That's why I've stopped.
So we can divide by alpha square and take the limit alpha
Okay.
to 0.
What will happen to the second term?
The second term will be 0.
By definition, what does little of alpha square mean? That is growing slower than alpha square. So if I divide and take the limit, by default it goes to 0. So that is why the first term itself is greater than equal. So you take this guy off here, divide by alpha square, take limit alpha going to 0. It'll give you that d transpose X star. We're far too used to this. It's just that in higher, like in multi-dimension, you need to write in this particular way. We've been doing this forever, right? Minima, look at the second gradient. If it is greater than 0, it's minima. If it's less than 0, it is maxima. So everything will hold as it is with signs changed. If you are looking for a maximization problem. Okay, so now let's start to look at some examples.
You can consider the converse also, right?
What converse?
That for some x term,
Mhm.
we find that HDN is
This doesn't hold in the converse.
this.
This also holds.
That is, I was trying to see from the.
Does it hold or not? Because there is an example here which for this doesn't hold. What are you trying to say? That if this is true, then definitely X star is a
Yeah.
okay. Why?
No, that is true, right? If it is a local minima, then the Hessian will be CST.
Yes.
Yeah, I'm talking about the converse. If for some X star, the Hessian is PhD,
Mhm.
then at that point we can claim that there is a local minimum.
Okay. How? Do it in your and show me later. If it's, we'll see if it's true. Okay. So it's time for some examples. Will tell us something interesting. Look at minimize 1 plus x over 2x for x greater than equal to. I'm just trying to attract your attention to something. That's why I've taken a constraint set. So bear with me for the moment. What do you think is happening here? Can you solve this problem? And okay, why?
Because both are increasing and the denominator is increasing faster.
Yeah, so it's going towards 1 by 2, right? So how can it be minimum be 1? What's the answer? One by two? No, so try to identify the difficulty. There's a reason I wrote that. Can you give me any point x star at which it is 1 by 2? You know it is lower bounded by 1 by 2. But can you give me an x star for which it is equal to 1 by 2? You can't. So it's essentially min is not achieved anywhere. So all you can say is a soup. You can't say min. Is the point clear? Okay, construct me another example of this type. Mm. Mm, 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 mm. Okay, similar behavior, right? Yeah. So what this did was that the domain was unbounded. Your example also is unbounded. Can you give me a bounded domain and this behavior? This will just hit at the heart of it, that nothing what we expect is guaranteed. Hold on. Because we're trying to do minimum, right? We're not trying to ask for inf. Inf is a complicated business. So can you make something like this happen even on a bounded domain where you don't achieve the inf? That's all I.
Minimum. what the interval multiplied with the square root of that.
I don't even know what to write 10 table. Why don't you give me something simple? I've completely forgotten what 10 of 0 was or 10 of 5 by 2. You guys remember? To tell me, I have forgotten. If you ask me to do integral 10 of x, I don't know what it is. Sin x, cos x, I can stop at that. 10 is a difficult beast. Or attempt something. It's not difficult. So this was an unbounded domain, and there was a problem. Let's look at bounded domain. Suppose it's between 1 and 2. Can you create a function for me where you can't achieve the min? What about 1 by n? It's like the simplest thing. What happens to 1 by n? Let's look at 1 by x. If I minimize over anything which is open, what happens? This again, the inf is 1 by 2, which is never achieved. So it's not only the problem that the domain is unbounded, I'm going to run away to something. This could easily happen even on an open set. Yeah.
So it is just open interval 1 2.
Yeah.
And it is like 1 by x minus 1 into x minus 2.
Why is it any different than this? You're giving a different class. This is the same class. Right? Class is same. I can write, but that's not going to serve our purpose. So what I want to state is a theorem by, or let's call it theorem itself. Okay. I won't prove it here. If you cannot find the proof, ask me. This will just tell you at least for what functions and what domains we are guaranteed to find minimum. Let f of x be a continuous real valued function on the compact. That's the most important part. Non-empty. Subset. Then let's call it f here. Then f contains a point that minimizes f of x. Is the statement clear?
Yes.
Okay. So what is it precluding? It's precluding something. How is it precluding these examples on the top?
Because the domain of the common.
Okay.
Basically in the compact domain. And
So-
if something actually is there.
Essentially think of closed
Bounded.
and bounded. That's what essentially you need. So this was not,
Bounded.
and this was not.
So
If you put them together and create a closed and bounded, then you're guaranteed to. I would like, yeah, try to prove this. It's not going to be a homework exercise, but just see if you can show something like this. All you need, in the simplest, you take n equal to 1. Take real life. If you don't or you're having trouble, ask me. I will come and help you. Okay. So this is what really you need if you're interested in really minimizing these functions. All right. But doesn't mean that necessarily it will not work if these conditions are not guaranteed. All this is telling you is that if this is true, then definitely it's good. No, so let's continue. Question? Yes, that's exactly what it is. And if this is true, then fx minimize f of x over capital F will always achieve minimum. Okay. Now let's go back to our condition here and here. So remember, if x is local minima, it has gradient 0 and a positive semi-definite SE. Now let's take an example here. So we're going to exercise those two necessary conditions to deduce something about the optimizer of this particular function. This function is not going to be any nice convex function, but still we'll be able to tell you what exactly it is optimal point. Just by those two necessary conditions. Half x1 square plus x1 times x2 plus 2x2 square minus 4x1 minus 4x2 plus, sorry, minus x2. Ugly looking function, but there's something interesting happening. So suppose I want to find the local minima of f or other minima of f. So far, what have we developed? That a minima should satisfy something. Can you use that to find me an exactly one minima for this? Unconstrained. Valid question? Looks, see, definitely not a convex function. So don't even attempt anything of that type. You learned something very limited today. That should be enough. Did somebody tell me the gradient? Somebody tell me the gradient. Should I do it? Check if it is what you get. This is x1 plus x2 minus a 4 and x1 plus 4x2 minus 4 minus 3x2 square. Everybody got this? Okay. What do I need to do? So I need to equate this to 0. What does it mean? Individually, this be 0 and this be 0. So what are the candidate solutions for x1, x2? Implies x1 plus x2 equal to 4, essentially. This clearly tells you something like this. And what else? You somehow eliminated others. Yeah, how did you do that? Oh, you wanted, okay, so that's another way. So implies x1 is equal to 4 minus x2. So this will give you 4 minus x2 plus 4x2 minus 4 minus 3x2 square equal to 0. So this gives me 4 cancelled. This is 3x2 is equal to 3x2 square. So this implies, and x1 plus x2 is 4. So what are the two possible answers for x1, x2? 0, 3. Okay. Now comes the second power given to you. What is the Hessian? Did anybody compute the Hessian? If not, I'll write it down. Just save time. So the F is interesting. All these nice terms and then a 4 minus 6x2. Those three entries are easy to check. Don't take a go. This will give you a 1. Rest of them are all x2. x1 appears only in the linear term, so that will disappear. Similarly, you can do the cross. This cross will give you a 1. That's the only cross. So it will give you both ones. And then the final term, because of minus 4, this will disappear. This is the only term which will give you something, and this is another term which will give you something. That's what. Okay. Okay. So now the two candidates for optimal choices were 4, 0 and 3, 1. What do I need to check? Say it clearly. So x1, x2, possible choices are 4, 0 or 3, 1. So what are the second derivatives at 4, 0? 1, 1, 1 and okay, and or what is this? 1, 1, 1 and minus 2. What kind of matrices are these? What do I need to show? That this has to be positive semi-definite. So for all y transpose del square f at 4, 0, this is greater than or equal to 0 for all y. Which of the two you think is either, neither?
The first one is positive semi-definite.
Okay.
Second one is not.
Why not?
If we choose 0, 1 point, the vector one. If we just multiply. So basically, the coordinate that I'm getting.
We get is 1 minus 2, right? If you multiply 0, 1 transpose, you'll get just simply the second row. What is the y you're taking?
0, 1.
0, 1. So that should get you only the second row
Yes.
multiplied by 0, 1 again. So it will give you minus 2. Okay. So,
That is not very.
only among these two, only one satisfies. So what is our conclusion? See, everybody's saying a different thing.
So the global minima is.
What do you want to say? We need 4 different versions. So start with. It's okay to have 4 different versions. Don't hesitate. Whatever is. There is a minima at 4, 0. Okay. What do you want to say?
If there is a minimum, then it is a local.
Okay. What do you want to say?
There is a local minimum.
Okay. What do you want to say?
Global.
There is a global minima at 4, 0. You see, I told you there will be many different versions. What did we prove? That if x star is a local minima, del f x star has to be 0 as well as the Hessian has to be positive semi-definite. Where did I get the guarantee that in fact it is true? We don't give any sufficiency condition, right? So all there is at most one candidate now left. So after all we have done, we have eliminated all other possibilities except for one possibility, which is 4, 0. Right? Hopefully the difference is clear. We've not proved sufficiency yet. He was demanding sufficiency, but we haven't done so. So all we have said is, if there is a local minima, then it has to be only at 4, 0. Okay. Now we'll go to the sufficiency part, and we'll see what happens to this example after we prove the sufficiency condition. What do you expect to happen? Only in terms of gradients and the Hessian? We expect that if for a point x, the gradient is 0 as well as it is positive semi-definite, then x is a local minimum. Is that what you expect to happen? That's what you're after, right? You're after the converse, saying if gradient is 0 and the Hessian is positive semi-definite, that point should be local optimum. Are you still standing by it?
The America is something. It's not really.
Let's take examples to check sufficient, not sufficient. It won't prove anything, but at least will satisfy our understanding, like how proceed. So let's take f of x to be x1 square plus x2 square. I'm choosing it for a good reason. So any point which has the gradient 0 and Hessian positive semi-definite, what do you expect to happen? This is a very nice function, knowing what we know from convexity. X1 square is convex, x2 square is convex, so addition is convex. And it's actually strictly convex, it's much nicer. So what do you expect to happen? From whatever you know from convexity. For the moment you're allowed to use it. Suppose it's just f of x is equal to x square. This we have been doing forever. We went ahead and checked the point. If it has gradient is 0, its second derivative is greater than 0. There is no Hessian, one dimension. Right. Something similar might happen here. So the simplest counterexample to start thinking about whether things might go wrong is the following. This function is no longer convex. Now can you show me that the gradient being 0 and the positive semi-definiteness of the Hessian is not sufficient to guarantee that the point is a local value. Let's just do it. What's the gradient of f(x)? What's the second? Hessian? This is 0. This is 0. Okay, so what are our candidates which you're interested in? What's the obvious choice for x star? Just look at this. Let's take x star to be 0. Does it satisfy first condition? Yes. Del f of x star is 0. What about the positive semi-definiteness? Clearly it's true because it's just 0, 0. Whatever you multiply to 0, 0, it'll end up being 0. So it satisfies the inequality y transpose del square f of 0, 0 y. Now try to find whether 0 is a local minima or not. If it was x1 square plus x2 square, everything what I've done will remain the same. And in fact, it is a local minimum. Because of the x1 cube, something has changed. What has changed? As I go negative, what happens? It decreases. So 0, 0 is in fact not a local minimum, while the conditions are true. So what does it refute? Your converse. So for the moment, we don't have the converse we would have liked. That del f x star is 0 and this is sufficient. So what we'll have to prove is that if I remove this,
on the level, like if the function will still increasing, I can actually for that particular function.
what are you?
For that particular function that you have chosen,
Yes.
it will just increase a near bit of 0 and then goes down.
What is there to now challenge? We have gradient 0, Hessian positive semi-definite. But still the point is not local optimum. So clearly the converse doesn't hold. We never said the converse was true for a convex function. You so far said nothing about the function being convex. Don't tell me that if it is a convex function, then it's true. I'm not trying to prove that yet. What is this example a refutation of? It's refuting something. What is that something?
No, I'm not talking, I understand that the function is decreasing, like,
No. What is it the refutation of? Just say it so that it's clear. This example is refuting something. That if you wanted the sufficiency conditions to be that the gradient is 0 and the Hessian is positive semi-definite, that's not going to work. That's what this is refuting. Okay, now what do you want to say?
I understand that for the particular function,
Yes.
the variable within the function, it should attend at local minima at 0, 0.
It is not, that's what you've proven, right? What else will be shown?
No, like, during, at the very close neighborhood of 0, the
Right.
excess cube grows much smaller than the
Where is the question of smaller, not smaller? What is its value at 0, 0?
0.
Now give me a neighborhood of 8 for which it is smaller than 0. So that we can stop this. Does there exist a point in the neighborhood of 0, 0 for which the function value is less than 0? No. What kind of function is x1 cube?
It's decreasing after 0.
Yeah.
I'm saying that at the very close neighborhood of 0, whatever the negative part of x1's cube,
Hmm.
it is not grows as x square.
Okay. So
So I'm saying that we can sure that if we take a neighborhood around 0, a ball more than radius 1, then obviously the function is decreasing. Or at many points it will be decreasing, giving the value negative.
okay.
I'm saying near to the, if we take a very small ball of 1 by n,
Hmm.
n is very large, then the function stays positive.
So what are you saying? Punchline.
Yeah, so the local minima is there at 0, 0.
Okay. Why is it not there at 0, 0?
Because if we fix x2 is 0, then function behaves as x1
Got it?
along that axis. It is strictly decreasing.
Okay. All directions.
That's why it's very carefully chosen to be a two-dimensional function. It will not work in one dimension. If I just take x1 cube, there's no freedom to go in that one fixed direction. Is everybody okay? 0, 0 is not a local minimum. So always say the punchline first. If you're telling 0, 0 is a local minimum, say that first.
All directions.
Yeah. No. So if a long argument, I get lost. So just first say that I claim that 0 is local minimum. Then I can at least try to convince you it's not. Okay, so now the sufficiency condition will be that I need to make this inequality strict. That's all. That if it's not 0, then I'm guaranteed. Okay. Lemma. If x star is 0 and is PD, then x star. Well, okay, how should I show this? Sorry? Taylor. Okay, what will happen in Taylor?
Keep the x star, x minus or plus equals to x star plus epsilon square a y transpose Hessian of x star 1 plus order of epsilon cube. Now, if x plus minus fx star equals to y transpose. So all I need to show that epsilon square y transpose is here. Y plus epsilon square strictly is positive.
Mhm.
So all I need to show that the second vector plus order of epsilon square that is strictly positive.
You go on. I will stop you.
Yeah, so, y trans Hessian is greater than strictly greater than 0. So we are multiplying epsilon square with it
Mhm.
and adding both sides by order of epsilon square terms.
Okay.
So this is whole term at in the limiting case, whole term is the strictly greater than changed by greater equals to at the limiting case.
Mhm.
And if from a Taylor expression, I know that
Tell me. Let's go to the next page. What do you want to write?
so y trans. Okay, let's look at first Taylor expression.
Hmm. F
F
of
of x minus
this minus or outside?
no point x plus the first epsilon my bracket close minus.
See, this will not work. You'll have to epsilon d is required.
Okay, epsilon d
Yeah.
minus fx equals to epsilon square y transpose
Y transpose.
d transpose is yes
Mhm.
d by that
What should I do?
plus order of epsilon cube
Cube.
epsilon square. Yes.
Okay. Fine. I have so far so good.
Yes.
What
Now
about
we
to
have-
the you already taken off the gradient term because it's 0.
Yes.
Okay.
And now we know that D transpose
This part
is
strictly
strictly.
okay.
Now, if I multiply with epsilon square, that's still now I'm only trying to figure it. I want to prove that that other side is greater or equal to 0.
Yeah.
That we need to prove this.
Yes.
Yes. So if we multiply by epsilon square,
Mhm.
then also the strict unit will be there.
What should I multiply?
Epsilon square.
To everywhere.
No, I'm talking about the particular term now.
This is epsilon square times some positive quantity.
Yeah.
Yes.
Now I am adding order of epsilon square both sides.
Okay. What? Positive, negative. Order will be negative also, right?
Yeah, positive.
Okay, so
And look at to the limiting case.
yeah, what will happen?
It will be greater than 0, greater equal to 0.
That I am not convinced. Anybody convinced? What are you doing? First of all, you're adding, let's say, g of epsilon and plus a g of epsilon, right? Where g of epsilon is order epsilon square or little of epsilon square.
Little.
Little o. Okay, now what? By adding and subtracting, what have we achieved?
Yeah, means I'm saying that it will whatever small I'm adding both side, it will not go to the negative side.
I have no clue what you're saying at this point. That's what you're supposed to stop. Right? People see the problem. This quantity can be negative. All you have to show is that this quantity dominates that negative. This is positive. That's all we really need to do. What he's trying to do, I don't follow how that is going to be achieved. But that's what I actually want to do. And remember what I want to show. I want to show it for a neighborhood. I'm allowed to choose things. So choose whatever you want to choose. But it is positive, semi-positive definite. What is the smallest value that D transpose Hessian times D take? Hessian is symmetric. For symmetric matrices, what do we know? Symmetric matrices split like U transpose D. This is the eigenvalue decomposition of a symmetric matrix. What is that? U Hermitian D U. And what is that D? The diagonal matrix. What does it consist of? The eigenvalues of it. So when we know it's positive definite, what is the smallest value this can take? You know this very well. When does this, for a positive semi-definite matrix, what is the smallest value that can take? 0. So by saying that it's positive definite, what are we actually doing? We're somehow saying something about the diagonal vector of this UD U Hermitian. What is that UD U Hermitian? Suddenly become from 0. What? I know that you know it. You're just not saying it. What is the minimum eigenvalue of a positive semi-definite matrix? Not necessarily, but what's the bound? It's 0. So similarly, for a positive definite matrix, what's the bound on this quantity? Just the minimum eigenvalue. You know it. You know this. So D transpose square fx D is greater than or equal to lambda min for any matrix really. It's true, given that it's positive definite, this quantity is strictly greater than 0. That's all. If you know, you can use this fact. It's not just greater than 0. It's actually, you know something about that. Or instead, you could have taken some value alpha strictly greater than it won't change anything. But this is actually what you know. You know that this is the minimum eigenvalue of this. For the rest of the proof, it not matter that there is some special quantity about the matrix. All you really need is some quantity which is strictly greater than 0. That's all you need. And then depending on that, because this is independent of, that's the most important thing. This number is independent of D. That's the most important point. whatever that quantity is, which is bounding it away from 0, is independent of D. For all D, that is true. That's the most important point. And that in particular, it is equal to lambda min. See here, you could mistake it for saying possibly it depends on D. It doesn't depend on D. That's the crucial fact. So use that and finish the argument.
So I would probably.
It's okay, just tell me, does the fact,
Yeah, that is clear.
okay, no, not clear. Do you use that or not?
I use only the limiting argument.
Okay, we'll wait. Can somebody finish the argument now? That this quantity is greater than or equal to lambda min, which is greater than 0, irrespective of what the D is.
This little of epsilon square term ultimately becomes smaller than lambda min epsilon square.
Lambda min epsilon square, you can say it slightly different. Let's look at by epsilon square. That's what the ratio is. So as epsilon goes to 0, eventually this will become smaller than lambda min, because lambda min has nothing to do with any of this. So that is true. So let's call it sum for epsilon less than alpha bar. This is true. Epsilon bar. For all epsilon smaller than epsilon bar, let this be true. So have I finished the argument? What is this term? This is epsilon square times lambda min. This is order lambda, order epsilon square, which is in scaling smaller. So what should I do? Give me the final line and we're done.
So the total sum is 0.
That's all I wanted to show. So the punchline really is that this has to be independent of the choice of D and epsilons. If that is not true, then whatever I'm going to do is not clear. See here, that is why this strictly greater is important. If it was 0, all I get is an order epsilon square term, which could be negative. Order epsilon is not guaranteed to be positive. All it says is as this ratio goes to 0, as epsilon goes to 0. That's all it says. Is this clear? Absolutely clear. So always remember, for sufficiency, don't apply the positive semi-definite test. You have to apply the positive definite test. And we have a concrete example where it actually doesn't work. It's actually informative example. It's constructed in a very clever way. You need 2 dimensions. It won't work in 1 dimension. In 2 dimensions, you will take a convex concave combination, which takes negative values also. If it only takes positive values, most likely it won't work. It's like eliminating many choices, which will make it a local minimum. Okay, let's stop it today here.